by doing things like analysing past chess games that were played by humans. They could be provided with simple chess strategies, but then use something like a traditional reinforcement learning approach, where they can identify patterns in moves that were more likely to result in winning versus moves that were more likely to result in losing the game to hone their performance. But now with deep learning, we're able to create machines that can learn chess in a fashion more like how humans learn it, by playing. A deep learning machine could be given the most basic rules on how chess is played and use its complex layer-based iterative approach to learn its own chess strategies and recognise patterns several orders of magnitude more complex than a traditional machine learning model could. The deep learning models in use today rely on things called artificial neurons. These are math functions that receive inputs and sum them up to create an output. Work on artificial neurons began back in the 1940s. However, it wasn't until technological breakthroughs in the 2010s that enabled artificial neural networks to be used in real environments. In an artificial neural network, each layer summarizes and feeds information to the next layer, ultimately producing a final output or prediction. During this process, the model derives the features itself. Now, we've talked about features, their importance, and how they're used in classical programming. Let's look at how the use of features evolved from classical programming to machine learning to deep learning. As we've established before, in machine learning, the features are manually selected and engineered, and then used to train and develop the model. But in deep learning, the features are automatically derived by the artificial neural network itself during the training and tuning process. The performance of the model based on that training is then fed back into the artificial neural network iteratively until generating the final model. Let's break this down into a more concrete example of a deep learning analysis of an image. In this example, we see the machine starts by identifying specific features of the input beginning with pixels. From there, it identifies edges, corners and contours, and object parts before making a prediction as to what the object is. In this way, it's extracting features like edges, corners and parts automatically based on the algorithm and the data it's being trained on. It can identify patterns at levels the human eye can't easily identify. As we mentioned before, the premise for deep learning started in the early 20th century, but the impact of improvements made in the field was really felt in the early 2000s. The big shift began with the ImageNet Large-Scale Visual Recognition Challenge, or ILS-VRC, which was a competition where research teams submitted programs that classified and detected objects and scenes in photographs. In 2010, the first year of the challenge, the winner of the challenge had a model with an accuracy rate of 71.81%. In 2011, accuracy improved marginally to around 74%. In 2012, when deep convolutional neural networks, common in deep learning models, started to be used, the accuracy rate jumped to about 82% and has been steadily climbing ever since. Then, in 2015, the winning program actually exceeded human performance at these narrow ILS-VRC tasks. Let's now pivot towards the machine learning pipeline by walking you through the phases of the pipeline. So to begin, you should always start with the business problem you or your team believe could benefit from machine learning. From there, you want to do some problem formulation. This phase entails, in part, articulating your business problem and converting it to a machine learning problem. We'll get into more detail later on, but for now, let's just talk generally about what's going on. After you've formulated the problem, you move on to the data preparation and pre-processing phase, which includes a few aspects. Data collection and integration, in order to ensure your raw data is in one central, accessible place. Data pre-processing and data visualization, which involves transforming raw data into an understandable format and extracting important features from that data. All this is done to ensure that your data is formatted correctly for your machine learning algorithm and that your data is cleaned up in a way that will maximize your model's prediction power. Once these steps are complete, you are ready to train and tune your model. This is an iterative process that can be performed many different times throughout this workflow. Initially, upon training, your model probably won't yield the results that you might be expecting. Therefore, you'll perform additional feature engineering and tune your model's hyperparameters before retraining. This cycle is repeated until your model's evaluation shows it's performing at the level required by your business case. If your model doesn't meet your business goals, you'll need to go back and reevaluate a few things. Take a second look at your data and features for ways to improve the model and the way that it's produced. Building a model is usually an iterative process in this way. Once the retraining happens and you're satisfied with the results, your model is deployed to deliver the best possible predictions. The bulk of the discussion to follow is designed to walk you through these different phases and give you practical examples of each stage. So let's start with an example close to home for us here at Amazon. Several years ago, Amazon needed to improve the way it routed customer service calls, so it looked to machine learning for help. The original routing system worked something like this. A customer would call in and was greeted by a menu. Press 1 for returns, press 2 for Kindle, press 3 for, well, you get the idea. The customer would then make a selection and be sent to an agent who would be trained in the right skills to help the customer. During the problem formulation phase of the pipeline, Amazon determined that the current routing system was problematic. Thinking about Amazon, you may be able to guess that we do and sell a lot of stuff here. And so the list of things a customer might be calling us for is, well, just about endless. So if we didn't play the right option to a customer calling in, the customer might be sent to a generalist or even to the wrong specialist, who then had to figure out what the customer needed before finally sending them to the agent with the right skills. Now, for some businesses, maybe that's not the end of the world. For Amazon, dealing with hundreds of millions of customer calls a year, it was pretty inefficient. It costed a lot of money, wasted a lot of time, and worst of all, it was not a good way to get our customers the help they needed. So the business problem that was articulated at this phase was focused around figuring out how to route customers to agents with the right skills and, therefore, reduce call transfers. To solve this problem, we needed to predict what skill would solve a customer call. Converting this into a machine learning problem made it identifying patterns in customer data that we could use to predict accurate customer routing. Based on the wording of this machine learning problem, it was clear that we are dealing with a multi-class classification problem. Since we wanted to base our predictions on past data from customer service calls, we were dealing with supervised learning. We eventually would train our model on a bunch of historical customer data labelled with the correct customer agent skills. That enabled the model to make its own predictions on other similar data moving forward, predicting, say, that a customer call needed a representative with a Kindle skill. The data we needed came from answering questions like, what were customers' recent orders? Did customers own a Kindle? Were they Prime members? The answers to these questions became our features. We then moved on to the data preparation or pre-processing phase. This phase includes data cleaning and exploratory data analysis. Now, a lot was done at this point, but one example of the data analysis undertaken was to think critically about the labels we were using. We asked ourselves, are there any labels we want to exclude from the model for some business reason? Are there any labels that are not entirely accurate? Are there any labels similar enough to be combined? Finding answers to some of these questions by exploring the data would help cut down on the amount of features being used and simplify our model, improving prediction accuracy. An example of what may have been found during this analysis was instead of having labels representing multiple Kindle skills, it made more sense to combine those skills into one overarching Kindle skill label, so that every customer who had a problem with a Kindle was routed to an agent trained in all Kindle issues. Data visualization was the next step, where we did a number of things, including a programmatic analysis to give us a quick sense of feature and label summaries, helping us better understand the data we were working with. At this point, we may have noticed that 40% of calls were related to returns, 30% were related to Prime memberships, 20% were related to Kindle, and so on. Important information that gives us a better sense of the data we're working with. We then moved on to feature engineering. We had some features that answered questions like, what was a customer's most recent order? What was the time of a customer's most recent order? And did the customer own a Kindle? When we feed these features into the model training algorithm, it can only learn from exactly what we show it. Here, for example, we are showing the model that this purchase was made at 1 p.m. on Tuesday the 13th. Unless we want to predict something really specific, or we're doing a time series analysis, that might not be the most meaningful feature to feed into our model. It would be more meaningful if we could transform that timestamp into a feature that represents how long ago the order took place. Knowing, for instance, that your last purchase was months ago will probably help the model realize that your last purchase probably isn't related to the reason that you're calling us. We can engineer this feature quite easily by just taking the difference between the order's date and time and today's date and time, giving us a much more helpful feature. A big part of preparing for the training process is to first split your data to ensure a proper division between your training and evaluation efforts. Think about it this way. The fundamental goal of machine learning is to generalize beyond the data instances used to train models. You want to evaluate your model to estimate the quality of its predictions for data the model has not been trained on. However, as is the case in supervised learning, because future instances have unknown target values and you cannot check the accuracy of those predictions for future instances now, you need to use some of the data that you already know the answer for as a proxy for future data. Now that's a lot of words. Essentially, what we want to do is withhold some data we know the answer for and not use that to train the model, but instead use that to test or evaluate the model. Evaluating the model with the same data that was used for training is not useful because it rewards models that can remember or memorize the training data, as opposed to generalizing from it. A common strategy is to split all available labeled data into training, validation, and testing subsets, usually with a ratio of 80%, 10%, 10%, or another common ratio is 70%, 15%, and 15%. After running a training job, we evaluated our model and began the process of iterative tweaks to the model and our data. For instance, we performed hyperparameter optimization. We tweaked the learning parameters to control how fast or slow our model was learning. Learning too fast means the algorithm will never reach an optimal value, while learning too slow means the algorithm takes too long and may never converge to the optimum in the given number of steps. Once we were happy with how the model interacted with that withheld or unseen test data, we deployed the model into production and monitored it to make sure that our business problem was indeed being addressed. Our problem was predicated on the assumption that the ability to more accurately predict skills would reduce the number of transfers a customer experienced. That was put to the test after we deployed, and the number of transfers did decrease, resulting in a much better customer experience. So looking back at the business problem we were trying to address, being figuring out how to route customers to agents with the right skills and therefore reducing call transfers, it looks like we've been successful. So, where to from here? AWS Training and Certification provides several training offerings to help you learn more about artificial intelligence and machine learning. head across to AWS Skill Builder, where you can find free, self-paced digital training courses covering a variety of topics, including machine learning. We also offer instructor-led classroom courses, such as the Machine Learning Pipeline on AWS, which you can find more about on the AWS Training and Certification website. Finally, if you don't know where to start, check out the Machine Learning Learning Plan on AWS Skill Builder, which brings together a variety of our machine learning courses in an easy-to-navigate learning plan to help you map out your learning journey. In this session, we talked about the basics of machine learning, starting from what is machine learning, through to the types of machine learning, what is deep learning, and finished with an overview of the machine learning pipeline. I'm Matthew Purcell, and it has been my pleasure to bring you this presentation. I'll be back to present another session later today all about generative AI, but up next, you'll have my colleague Arthi, who will present Accelerate Your Machine Learning Journey with Amazon SageMaker.
Hello and welcome to the session, Accelerate Your Machine Learning Journey with Amazon SageMaker. My name is Arthi Natarajan, Senior Technical Trainer here in AWS Training and Certification. Building a machine learning model is a complex, time-consuming process. In this session, you will learn how Amazon SageMaker helps data scientists, developers, and machine learning experts to quickly and cost-effectively start building, training, and deploying models. SageMaker takes the heavy lifting out of machine learning, allowing teams to focus on more important objectives and accelerates the process of building ML solutions. So let's get started. Today, there are tens of thousands of customers using Amazon SageMaker, making it one of the fastest growing services in the history of AWS. Not only is ML used for a wide variety of use cases such as churn prediction, predictive maintenance, computer vision, natural language processing, and fraud detection, but today more and more organizations are looking to solve real-world business problems to enable faster and better decision-making, optimize the business processes, and accelerate innovation. Amazon SageMaker is a fully managed machine learning service enabling business analysts, data scientists, and MLOps engineers to quickly and easily build ML models for any use case regardless of ML expertise. Data scientists can easily prepare and build, train, and deploy ML models using Amazon SageMaker Studio. Business analysts can make ML predictions using a visual interface with Amazon SageMaker Canvas without any ML expertise. And finally, we have ML engineers who can deploy and manage models at scale with SageMaker's MLOps capabilities. AI ML adoption is not easy. Customers tell us there are several key challenges in building successful ML solutions. Firstly, today, there are not enough people with ML expertise to meet the growing demand for building with ML. Next, data scientists are overwhelmed by the proliferation of data science tools that are difficult to integrate, siloed by each part of the ML lifecycle. Moreover, model training is an iterative process, costs arising from multiple training iterations, choice of infrastructure, frequency of inferencing, all of which have often been a barrier to implementing successful AI implementations. And next is the lack of agility in machine learning workflows. DevOps teams have to manually manage disparate environments for prototyping, development, testing and production, making it really difficult to maintain consistency across these environments and ultimately delaying deployment of models to production. And as we all know, data fuels ML. But when data needs to be labeled and prepared in large volumes before it can be used for training ML models, this requires massive data processing capabilities. Let's take a look at how SageMaker helps customers to address these challenges. SageMaker makes ML accessible to everyone. It even provides no-code ML tools such as SageMaker Canvas to enable business analysts with no ML expertise to leverage machine learning. SageMaker brings together purpose-built tools for every step of the machine learning lifecycle under the SageMaker Studio integrated development environment, making it easy to build, train, and deploy ML models. SageMaker's high-performing, cost-efficient, fully managed infrastructure now enables customers to quickly train their models and deploy them without impacting their budgets. And SageMaker also provides MLOps capabilities, including SageMaker pipelines, SageMaker projects, and SageMaker model registry to help streamline the ML lifecycle, reducing the operational burden of managing ML models in production and accelerating the time to value. Finally, tools such as Ground Truth and Data Wrangler make it easy to label and prepare data for machine learning at scale. Let's now dive into how SageMaker boosts the productivity of data scientists in building machine learning models. Let's set the stage by talking about the typical ML workflow. We have 4 steps here. We typically start by preparing your data. High-quality data preparation is critical to high-quality model performance. Data scientists can spend 60 to 80% of their time actually on preparing data. Once you have your curated data set, next you move on to building a model. Here, you need to choose the right algorithm or framework for your model. Think about the environment for your training job. Whether the ML algorithm can scale to large datasets. Do you need to distribute the machine learning training job on multiple machines? And once your model has been trained, the next step is to evaluate and tune the model to deliver the most accurate predictions. And this can be a fairly cumbersome task as you experiment through different algorithms, different parameters to see how they change the model and impact the outcome. Finally, once the model evaluation meets business objectives, you integrate the model with your application and deploy this application to an infrastructure that will scale, and then you need to monitor the model in production. As we can see, building a model pipeline is a complex, expensive, iterative process. So data scientists are looking for tools to automate this complex workflow. What we really need is a centralized, integrated workbench that helps to orchestrate this machine learning workflow. SageMaker solves this challenge by bringing together tools for every step of the ML lifecycle under one unified visual user interface, namely Amazon SageMaker Studio. It is the first fully integrated development environment designed specifically for machine learning that brings everything you need for machine learning within a single pane of glass. From a web-based visual interface, you have access to purpose-built tools for every step of the ML development, including labeling, data preparation, feature engineering, bias detection, training, tuning, hosting, monitoring, and even explainability of ML models. Using SageMaker Studio's integrated capabilities for machine learning, you can eliminate months of writing custom integration code and ultimately reduce the cost. At the core of SageMaker Studio's end-to-end machine learning development are SageMaker Jupyter notebooks. These notebooks are fully managed, can be easily launched in a single click, and come pre-configured with deep learning environments such as TensorFlow and PyTorch. You can collaboratively prepare the data, build, train, and deploy ML models using your preferred framework, and also monitor the deployed models from within your notebook through seamless integration with purpose-built tools and AWS services. SageMaker Studio also comes in with built-in integration with Spark, Hive, and Presto, running on Amazon EMR and AWS Glue interactive sessions to help you handle large-scale interactive data preparation and machine learning workflows all within your Studio notebook. And finally, you can easily scale your underlying compute resources up or down with a simple click. You can pick from the broadest choice of compute resources offered by AWS, including the most powerful GPU instances for machine learning. We all know data coming in from the real world does not look exactly like the data you trained your model on. Analyzing, transforming, and preparing the data for machine learning can be a time-consuming and tedious task, often taking weeks or even months. Data Wrangler, a low-code data preparation tool, enables you to aggregate and prepare the data for machine learning in minutes. With Data Wrangler, it is data preparation made simple and more intuitive, all from a single visual interface, so you can build better features and faster. With Data Wrangler, you can easily browse, query, and import the tabular data from different data sources such as Amazon S3, Amazon Redshift, Amazon Athena, as well as from external sources such as Snowflake and Databricks, and over 40 popular cloud-based applications such as Salesforce and Google Analytics. Once you've imported the data into Data Wrangler, it is simple to explore and visualize your data using robust visualization templates. You can then transform your data by applying point-and-click transformations from Data Wrangler's UI, leveraging an editable library of code snippets, or writing your own custom transforms. Using Data Wrangler, users can also generate a data quality and insights report that automatically verifies the data quality and helps you to detect abnormalities in your data. As you take these data preparation steps, Data Wrangler builds a visual diagram for you to revisit your work, and you can then export your data preparation workflow to a Jupyter notebook that you can then use in a training or inference pipeline. You can also choose to move on to building your model from the Data Wrangler by launching an autopilot experiment. Let's now explore the capabilities and benefits of SageMaker for training ML models. With SageMaker, you have a number of options for building an ML model. You can use a built-in algorithm provided by SageMaker. These algorithms, available in pre-built container images, are optimized for speed, scale, and accuracy, and can perform training on petabyte-scale datasets to solve a variety of machine learning problems. Some examples of these algorithms include general-purpose algorithms such as XGBoost, factorization machines for classification or regression problems, K-means principal component analysis for unsupervised learning tasks such as clustering, dimension reduction, and a suite of algorithms for text analysis and image processing tasks. Amazon SageMaker makes extensive use of Docker containers for build and runtime tasks. SageMaker provides pre-built Docker images for all of its built-in algorithms. But by no means are you locked into built-in algorithms. The second option is script mode. If you are building your own model using a machine learning framework that is supported by Amazon SageMaker, such as TensorFlow, MXNet, PyTorch, XGBoost, SparkML, lots of options out there. You can write a custom training script where you define your model in a Python file, and rather than trying to build a compatible custom container from scratch, you can simply run the model using one of the pre-built Docker images for the deep learning framework that is supported and managed by SageMaker. You can bring all of your requirements and dependencies in a requirements.txt file. Next, the third option we have is the bring your own container option. Here, if you are training with a model that does not have a supported built-in container image on SageMaker, well, then you can write your own Docker file that packages all of your code, dependencies, then build a Docker image locally and push that image to the Amazon Elastic Container Registry and point to this image in your training job. Lastly, we have a new generation of what we call as low-code, no-code ML options that enables building ML solutions without the need for extensive ML expertise or even no ML expertise. Firstly, we have SageMaker Autopilot that automates the data preparation, training and tuning, providing an end-to-end AutoML flow. In addition, we have SageMaker Jumpstart that offers over 150 trainable algorithms, pre-trained models, and one-click deployable solution stacks from the world of open source. And lastly, we have SageMaker Canvas, a no-code machine learning tool that enables business analysts with no machine learning expertise to generate ML models. Let's now take a more detailed look at how the core model training and deployment flow works. The Jupyter Notebooks should give responsive environments for interactive exploration. But does that mean they need expensive infrastructure? Contrary to the way that traditional Jupyter Notebooks are commonly run, where a single instance type handles all kinds of ML tasks, SageMaker training and inference run on a separate infrastructure from the notebook instance. SageMaker decouples the light tasks such as your data exploration, cleaning and preparation, from the heavier tasks such as model training and deployment, and runs them in different types of instances. According to this approach, you can execute the light tasks on a cheaper notebook instance, such as the T or M family, and outsource the heavy training or deployment jobs to a more powerful infrastructure. Example, a large GPU-attached instance. This way, you pay for the expensive infrastructure only for the exact duration of the training, while you pay much lower rates during the lighter tasks which run on the cheaper instance. The added advantage is that you can also now scale horizontally during training because you can select multiple instances to run your training jobs in parallel. Now, since the training job does not run in the notebook instance, this means the training data needs to be stored elsewhere that is accessible by SageMaker. And the most commonly used and cost-effective data store is Amazon S3. SageMaker uses containers for its build and run tasks. Containers are lightweight and portable across environments. SageMaker provides container images for all of its pre-built algorithms and supported deep learning frameworks. And as we explained earlier, if you are providing your own container, all you need to do to package your training code, dependencies, and configurations in your own container image and push this image to the Amazon Elastic Container Registry. And when you need to run a training job, you simply point to the right container image in your training job. Now, SageMaker SDK provides a high-level interface called as the estimator, and that handles end-to-end SageMaker training and deployment tasks. So when you start the training job by invoking the estimator.fit, SageMaker spins up a ephemeral training cluster, a collection of EC2 dedicated to your training job, and then wires your training code container and the training data from S3 and runs the training job on the ephemeral infrastructure that you have requested. So every SageMaker training job has its own training cluster. This means you have dedicated EC2 instances alive just for the number of seconds your model needs to train. Once the training job is finished, the trained model, that's your model artifact, is also stored in S3. And now we are ready to host the trained model. When hosting models in production, SageMaker manages the deployment of the inference instances. All you need to provide is the containerized inference code, specify the number of ML inference instances you need. You can also configure the endpoint to elastically scale the deployed ML compute instances. SageMaker then combines the stored model artifact with your inference code to deploy them on your requested infrastructure. When you specify 2 or more instances, SageMaker automatically launches them in multiple availability zones to ensure continuous availability. This creates a real-time inference endpoint using the REST API. Now note that the real-time inference is not the only inference option. If you don't need real-time inference and you have lots of data that you would like to inference in bulk, then you can instead run what we call a batch inference job. Let's now take a quick look at the code to trigger a model training job. The high-level SageMaker SDK that we use in our Jupyter notebooks uses a scikit-learn-like estimator syntax to define and execute the training jobs. In this example, as you can see, we're using the XGBoost built-in algorithm. In your estimator, you will specify your container image, the URI, and the execution role. You also specify the resources to provision, the output path for the trained model artifacts, and set the hyperparameters for the chosen algorithm. And finally, you trigger the training job by calling the fit method on the estimator while specifying your training and validation data. Now, once the training job generates your model, you can now deploy your model by creating a predictor and use that to make your predictions. Let's now take a look at how SageMaker helps with model tuning. When you build complex machine learning systems, like deep learning neural networks, exploring all of the possible combinations of hyperparameters is just impractical. SageMaker automatic model tuning, also known as hyperparameter tuning, accelerates your productivity. It finds the best version of a model by running many training jobs on your dataset, using the algorithm and the ranges of hyperparameters that you specify. It then chooses the hyperparameter values that result in a model that performs the best, as measured by a metric, again chosen by you. Now, early on, we discussed that organizations today want to use more machine learning in their businesses, but they only have so many data scientists and ML practitioners. And this is where low-code machine learning comes in to improve your ML practitioners' productivity and accelerates your workflow. Introducing SageMaker Autopilot. SageMaker Autopilot is a fully managed service that you can invoke with a single API call or a few clicks using the SageMaker Studio. It is going to help you automate the complete build, train, deployment cycle. So basically, to start an autopilot job, all you need to do is to provide your data in tabular or Parquet formats on S3. Your data is already labeled. You do not need to featureize the data. Autopilot will do this for you. You specify the target column. That is, what is it that you're trying to predict? And then we trigger an autopilot job in SageMaker. SageMaker Autopilot will first analyze your data set, determines what kind of machine learning problem is being solved, and then it runs a number of candidates. Each candidate is a unique combination of a feature engineering strategy with a model tuning strategy. So Autopilot figures out the optimal combination of data pre-processing steps, machine learning algorithms, and hyperparameters. And then it uses this combination to train an inference pipeline which you can easily deploy. SageMaker Autopilot also provides you full visibility and control. It generates the Python code and you get back a commented Jupyter notebook to reproduce the work, or you can use that code for further manual tuning if you are so inclined. In SageMaker Autopilot, by default, you are going to get 250 models trained. Now, SageMaker Autopilot is also integrated with SageMaker Experiments for trial tracking and leaderboards. And this provides you a nice dashboard where you can see model evaluation metrics and charts. Autopilot currently supports regression classification. Thank you all for attending this session today. I'm Aarti Natarajan, and it has been my pleasure to present this session. I will be back to present another session later today, but next up we have Matthew Purcell, who will present Unleashing Innovate, the Generative AI Revolution.